So my pleasure to introduce today's QuSCo on Air speaker, Dr. Anna Parker. She's currently the Director of Materials Optimization at NVISION Imaging Technologies based in Ulm. Dr. Parker completed her PhD and then postdoc in the group of Alex Pine at UC Berkeley in California, where she acquired her expertise in using NV centers in diamond for external hyperpolarization, and that's going to be the topic of today's talk. So take it away.
All right, so I will share my screen. And Alistair, could you just confirm? Oh, hold on one sec. Let me go back to the beginning. Just 1 second. All right, now let's give this another shot. Okay, now, Alistair, could you confirm that this is presenting?
Yes, it is, yeah.
Okay, all right, excellent. Yeah, so Alistair, thanks very much for the invitation and for the introduction. I thought this would be a pretty cool opportunity because I've been having a good time working with Alistair at Envision for over a year now, and we've been working on some NMR aspects of Envision's development together. So of course he's told me about like the QuSCo community, so I thought this would be a cool chance to meet you guys. And also since this is, I mean, certainly there's some overlap, but since this is sort of a chance to present your work and your field to a different field, I was very interested in your perspective and what kind of questions come up, and hopefully I can answer everything sufficiently. So just a bit more on my background. So as Alistair said, I did my PhD at UC Berkeley with Alex Pines. So Alex Pines' research group has a lot of history in the NMR community, a lot of there's some background noise, so I hope it's not too bad. But so the Pines group has a rich history with NMR, and a lot of significant developments in NMR happened in that group. And at the time when I joined, it was a really creative and a really knowledgeable atmosphere. So it was a great opportunity for me. So that's where I learned about NV centers and hyperpolarization, and there I was actually exposed to many different types of hyperpolarization. So just a brief sort of bit of information too. You'll see at the bottom that I have both Envision and UC Berkeley here. So I am a full-time employee of Envision, and I don't work at all for UC Berkeley anymore, but I thought it would be good to put that affiliation on there as well, because all of the work that I show here is from my PhD, so none of it is from Envision actually. So just wanted to make that part clear. So I also thought we can keep questions till the end, just for the sake of time. Just to let you guys know. So my goal of this talk was to introduce you guys to different types of hyperpolarization, just what I was exposed to. And I'm certainly not an expert in all these different types, but I wanted to provide, links and references just in case any of this sparks some scientific curiosity or some curiosity that you guys want to seek this out later, because there's a lot of really nice work and a lot of really cool research groups that are working on this type of stuff. I then would move in more specifically to what I did during my PhD. So the ideas that we had when designing this PhD project, and then that sort of led to us building like a first prototype of a home-built polarizer based on NV centers. And then of course we got some preliminary results before I graduated, and then I would give you our final outlook that we had at the time. And what we thought would be needed to really push this technology to be useful. So I'll just get started then with the hyperpolarization introduction. So whenever I refer to hyperpolarization, I'm always talking about in regards to magnetic resonance technology. So hyperpolarization is a technique that stands to vastly improve magnetic resonance imaging and NMR. And so of course, MRI is something that you can use to non-invasively image fluid or tissue or the human body in general. NMR is also a way to non-invasively get unambiguous information about molecules to macromolecular assemblies to proteins, just as a few examples. And so I think you can say pretty much without hyperbole that both of these technologies revolutionized both diagnostics and chemical analysis. And I don't think I need to say anything further about MRI, but for any of you who don't know or who aren't familiar with the impact of NMR, what used to take a chemistry PhD, like a full 5-year PhD to complete in the 1950s, now only takes 30 minutes by NMR. So it's something that has sort of been in, or it's something that is in the background, that works in the background of a lot of scientific research, but it's so fundamentally necessary for a lot of synthetic chemistry research and all of the applications that stem from it. So I just wanted to say, with highlighting these two things, one of the main advantages of these techniques is, or the reason behind it, is also the reason behind one of its greatest flaws, and therefore also why these techniques cost so much, and both in terms of like the equipment you need and the personnel that you need. So of course, both of these methods are based on measuring nuclear spin states. For MRI, you're looking at nuclei in the body or in tissue, or proton nuclei mainly in the body or tissue. In NMR, you look at various different nuclei like proton, carbon, N15, phosphorus, for example. And of course, so you're probing these spin state transitions, which are really low in energy. And that means that the RF excitation that you apply is also really low in energy. This means that you do no damage, but the problem arises because this energy is also much lower than thermal fluctuations. And it's these thermal fluctuations that make your sensitivity of the method extremely poor. So what I mean by this is, so if you can imagine, in magnetic resonance technologies, your typical detection is inductive detection with a coil and a resonant inductor capacitor circuit. So what you measure is an oscillating magnetization, which induces an oscillating voltage in your coil. So you can imagine that the more spins that you have aligned, the more net magnetization that you have, and therefore the larger voltage that you'll induce in your coil. However, because thermal fluctuations have larger energy than your actual NMR signal, these fluctuations totally ruin whatever net magnetization you can generate, such that even in state-of-the-art systems that have a magnetic field of 10 Tesla at room temperature, the polarization or the nuclear spin alignment of your protons is just 35 ppm. This is extremely weak, and if you were to ever calculate this number for a UV vis transition, for example, you always get 1. So this is something that you need to consider in NMR spectroscopy and magnetic resonance imaging, but not for other types of spectroscopies. And so I already mentioned it before, but this nuclear spin alignment is quantified in a term called polarization. This is the normalized population difference between the energy levels, and it comes from the Boltzmann polarization, actually. So this is the equation for determining polarization. And here, so typically this would just be h nu for the energy of the transition over the thermal energy. So you're comparing the energy of your transition to the thermal energy of the conditions that you have. And so for spin states, the energy of your transition is gamma times b, where gamma is your gyromagnetic ratio. So you can see immediately that if you want to increase your polarization, you could first increase gamma. And so this plot below here just shows the effect of increasing gamma. And of course, I also wanted to point out here that because the gyromagnetic ratio of electrons is orders of magnitude larger than that of all nuclei, then its polarization in most conditions is orders of magnitude larger. So that's why EPR is much more sensitive. You can also increase your thermal polarization by increasing the energy of your transition, by increasing magnetic field, or by reducing the thermal energy of your system, and therefore, and doing that by lowering temperature. So now that I've told you what, just one more point on this that I want to say is that this problem of polarization in NMR and MRI is the reason why you need such big, expensive devices, and why technology has developed towards larger and larger systems versus most technology that's been developed to smaller and smaller systems. And of course, there are other reasons to go towards high magnetic field, but sensitivity is a big reason, and people will pay a lot of money for that. Okay, so now I'll move on. So now that I've told you what polarization is, I would like to define hyperpolarization. And so I will say hyperpolarized spin state is one that has a larger spin polarization than what its current thermal conditions would dictate, where thermal conditions are your magnetic field and your temperature. hyperpolarization has the potential to give you dramatic sensitivity improvement. And I'm giving probably the best example here just in terms of sensitivity improvement. This is from a technique called dissolution DNP. I'll describe a bit more later, but this sort of maximizes the enhancement you can get. Sometimes you can get enhancements of 4 to 5 orders of magnitude. And so you can see that with this kind of enhancement, you can get much better information for a lot less time. And in a lot of cases for NMR and for MRI, you can get information that just wasn't there previously. So hyperpolarization can be, has the potential at least to be quite powerful. So just a super simple model of how hyperpolarization works. You start with a polarization source, and for us, this is a highly polarized spin state. And then you need to make contact between your source and your target, and a way of transferring polarization from one to the other. And the last, I kind of just put here as a formality, but you need a way to detect your signal at the end. And so most cases that I will discuss, this is just inductive detection with a coil, as I mentioned before. So what I will do is just give you all a few examples of what a polarization source could be, and then what how you could put your source in contact with you. So these are examples of polarization sources. These are the sources that I was exposed to when I was in the Pines group. So the first example that I give are stable radicals. These are molecules which have at least one stable unpaired electron spin that aren't reactive, because you want to be able to mix this with other molecules and transfer polarization to those other molecules. So basically these take advantage of the fact that the electron has a much larger gyromagnetic ratio than any nucleus. And this is the model that's used in that really nice example I showed earlier of dissolution DNP, which they can use for experiments like hyperpolarizing carbon on a metabolite and imaging that metabolite at low concentrations in the human body. The next example I would like to give are optically pumped alkali vapor atoms. So as you know, alkali elements have a single valence electron. And so if you take rubidium is a really nice example of this. So what you can do is excite one electronic transition of rubidium, for example. So I think one of the transitions for rubidium is 795 nanometer. But if you make this light circularly polarized, you can either add or subtract 1 unit of angular momentum, and by that way you can optically select a spin state of your electron. And so because alkali vapor atoms are quite reactive, this isn't actually a very diverse polarization source, but you can use these to polarize noble gases, because noble gases are non-reactive. So people have actually done this where you optically pump an alkali vapor atom, and then you flow a noble gas through a cell of these atoms, and you then can hyperpolarize noble gases. And then you have a polarization source that you can flow over surfaces and hyperpolarized surfaces. You can dissolve them in solutions. One really cool application that people are continuing to develop is you can use them to image lungs. So I have a reference here of I believe it's there are some research hospitals that use these noble gases to image lungs and are actually getting useful information about diagnosing lung disease with this technique. Yeah, and so then the next example that I have is parahydrogen. So these are gaseous hydrogen molecules, and you have 2 main spin states or 2 types of spin states that I will mention. And parahydrogen is a nuclear singlet state, and this is an anti-symmetric spin state with a total angular momentum of 0. And what's useful about parahydrogen is this singlet state is coupled to the rotational state of the molecule. So pretty much if you can change the rotational state of the molecule, and people do this by flowing hydrogen gas just over a simple catalyst like iron oxide at liquid nitrogen temperatures, you change it to the lowest rotational state, this locks it into parahydrogen state, and then you have a completely pure quantum state that's very nicely protected from any kind of environmental noise. And so people have used this for some really cool studies of spin physics. The last example I would give that you all are probably familiar with are optically pumped solid state dopants. So these are, the Enve is a really great example of this. These are systems of trapped electrons in solids. where just by a consequence of their energy level system, you can control their spin state with, or you can highly polarize and control their spin state with light. Yeah, so that concludes the examples of polarization sources I want to give. And now I want to give you an example of how to couple these sources with a target. And so the first example that I start with is coupling a polarization source, a stable radical, with a target that is just a molecule of interest. So with stable radicals, the trick is you need to be able to homogeneously disperse them in a solid. And so the way people do this are they use glassing materials like glycerol or tetrachloroethane, and they freeze them really rapidly to perform a glass or an amorphous solid. And this glass also contains the molecule that you want to polarize. So what happens here is you have an electron and a nuclear spin system, or in the simplest case, you have an electron coupled to a nucleus. These nuclei these spins are then coupled. And through this hyperfine coupling, your two spin transitions become weakly allowed, and you can drive these with microwaves. And so by driving these with microwaves, you can actually transfer polarization. So that's one example of putting a source in contact with a molecule and transferring polarization. Next example I'll give just briefly is you can optically pump, if you optically pump an alkali vapor atom and flow a noble gas through a cell of this, the polarization transfer actually happens by collisions between the atoms. And this figure shows two examples here where either there's a direct collision or you have a collision mediated by a buffer gas. And what happens is you get a transient Fermi contact interaction happening between the nucleus and the electron spin of the atom. And that drives transfer of the hyperpolarized electron spin polarization to the nucleus in the gas. The last example I give is parahydrogen, and you do this by actually physically adding the hydrogen to the molecule. Of course, you need a catalyst to do this. So there are two main, this is certainly not exhaustive, but you need there are two main or common ways of doing this, and that's either using the catalyst to add the hydrogen nuclei across a double or a triple bond of a molecule, and then you change the identity of the molecule, but what you get is a highly polarized nuclear singlet state that you can then probe with NMR, or you can transfer that polarization to another nucleus and measure that nucleus. The other option is you can use a different catalyst and a different class of molecules to exchange the hydrogen. So instead of changing the identity of the molecule, you just exchange out thermally polarized protons with a highly polarized singlet state, and then you can do all the same stuff. So that concludes what I wanted to, or the examples that I wanted to give for both polarization source and for how to make contact between the source and the target. What I want to do next is deep dive into just one example of hyperpolarization techniques, because this is what I use for my PhD. And so the technique that I focus on is this method of homogeneously dispersing electron spins in a amorphous matrix, creating coupling between your electron spins and your nuclei, and then driving two spin transitions with microwaves. So this technique has a ton of different variants, but largely you can call this dynamic nuclear polarization. And as I said, so this is the technique that I will end up applying to NV centers to hyperpolarize other nuclei with NV centers. So a few more points on this. So I said that it's the hyperfine interaction that enables you to excite two spin transitions. So this could either be a double quantum transition, which is a nuclear flip and an electron spin flip and a nuclear spin flip, or you can excite a zero quantum transition, which is a electron spin flip and a nuclear spin flop. So total angular momentum change of 0. And typically what happens is because the dipolar interaction and therefore transition probabilities of these types of transitions are very dependent on distance. Typically with your electron spin, you end up polarizing nuclei that are very close to the electron, so usually within a nanometer. And then, so what happens is you can polarize the nuclear spins that are close to the radical, and then just by homonuclear dipole-dipole coupling, you can get energy-conserving flip-flops between nuclei. And this actually creates a mechanism for polarization to spin diffuse away from your radical and into what is called the bulk, where the nuclei don't really feel the effect of the radical. So this phenomenon called spin diffusion is often just as important as the hyperfine interaction for really building up macro scale polarization. So the classic experiment that you would do to confirm that DNP is occurring is, you'd have your glass with your electron spin and your target molecule, and then you'd either fix your magnetic field and sweep microwave frequency, or you'd fix your microwave frequency and sweep magnetic field through the EPR transition. And this is a nice example, probably one of the cleanest examples you see of where a group did this. They fixed their microwave frequency and excited these transitions with cavity and swept their magnetic field. And if you monitor the NMR signal while doing this, you will see sort of an antiphase pattern of enhancement as you sweep through the EPR transition. And this is basically just, first, you encounter the lower energy two-spin transition, which is the zero quantum transition, or the difference between the electron and the nuclear spin, Larmor. And then as you continue to sweep up, you'll get to the higher energy two-spin transition, the double quantum, which is the electron spin Larmor plus your nuclear spin Larmor. So this is a classic curve that is evidence that DNP is really occurring in your system. Just to sort of summarize, I have the general steps of performing DNP, what you need to do. So first, you would disperse your electron in the matrix with your target molecule and couple the two systems. Then you would apply a magnetic field and temperature condition. So this basically sets the energy levels that you have to work with, and the temperature conditions set the dynamics that you have. So they set your nuclear T1 and your electron T1. And then these last two steps are something that ends up repeating. So first, your electron spin polarization builds, and then you excite these two spin transitions with your microwave excitation. And often what happens to work really well, and often what is necessary because you're at high fields where you don't have as much microwave power, is you just apply CW irradiation. So this step merges into one, and often that can actually work pretty well. The last step that we have here is then once you're exciting these transitions, your nuclear spin polarization will build, and the thing that works against you this whole time is your nuclear T1. And so in this case, your nuclear T1 is always the process of bringing your nuclear spins to thermal equilibrium. And so in the case of hyperpolarization, that's actually actively reducing your signal. So at some point, you will come to a steady state. And I don't want to go too much into detail on this. There's already enough to discuss, but I just wanted to highlight a few limiting factors for each step. So certainly one big thing that will limit your DNP enhancement or the polarization you can achieve is your electron nuclear coupling. So in most cases, the larger electron nuclear coupling, the better polarization you can achieve because you just have more efficiency when you in each transition that you excite with your microwaves. Then the next thing is your magnetic field. So often going higher magnetic field means more polarization because one, you get a longer nuclear T1, and two, you get a larger starting electron spin polarization. So pretty much for both of those factors, nuclear T1 and electron spin polarization, the higher pretty much always means that you'll get more nuclear spin polarization in the end. The last thing I will note, which I'm sure this group is quite familiar with, is your polarization efficiency. So I mentioned that you could just do this with CW application, but you can actually get quite sophisticated with the techniques you use. And of course, if you have more polarization efficiency, then you have more flexibility in the types of systems that you can hyperpolarize, because even systems with short T1, you can kind of get around that by just making each polarization step faster. Okay. So that pretty much concludes the introduction. So hyperpolarized nuclear spin state is one that has a polarization beyond thermal equilibrium, or what your magnetic field and your temperature would dictate. You can create hyperpolarized, or like a hyperpolarized nuclear ensemble, if you couple a highly polarized spin state to a target molecule, and then use some mechanism to transfer polarization. And for the rest of the talk, I will focus on dynamic nuclear polarization. and how we apply this to NV centers in diamond. Okay, so I think a lot of you are familiar with NV centers, so I make the introduction here quite brief. An NV center is one of hundreds of color centers found in diamond, where a color center is a system of trapped electron spins with sort of isolated energy levels from the diamond energy levels, and you can typically when you photoexcite them, these defects will fluoresce, and their fluorescence is sort of a signature of the color center. NVs are special of all of these color centers because when you optically excite them, you can actually control their electron spin. And this is a consequence of their energy level structure. So any NV, so the NV is a spin 1 with a zero field splitting, you can have some NVs just in the plus or minus 1 in the ground state, and any NV that you excite that's already in the plus or minus 1 state, if you optically excite this defect, then they prefer to fluoresce, or they prefer to relax back down to the ground state by inter-system crossing rather than fluorescence. And it is this process which ends up dumping polarization or population into this MS equals 0 state. So just by illuminating the NV with a laser, you can get a hyperpolarized electron spin state. And this is pretty powerful for magnetic resonance because you completely get around the need for a really high magnetic field or really low temperatures like liquid helium. And that just introduces not only the possibility for cheaper polarizers or cheaper devices, but also, excuse me, but also for just more accessible technology. So if you can make a cheaper device that's easier to use, then you can, more people have access to it, and potentially you can just do a lot more and study a lot more things. So it's for this reason that we were really excited about the NV when I started my PhD. But there were other reasons why we thought NVs in diamond specifically would make a good hyperpolarizer. And so one of the big questions that comes up when you want to do this is, how do you actually couple the NV to a nucleus outside in your target molecule? Like, how do you create that contact between NVs and nuclei outside? And the real problem here is NVs with really nice properties are typically deep in the diamond, a few nanometers at least, and often in DNP, the transitions you excite, the electron spin is about a nanometer away from the nucleus. So that means that the coupling is really weak, making transfer really difficult. So at the time, we thought it would actually be best if we use the NV to polarize a carbon-13 spin in diamond, and then use the carbon-13 to relay the polarization outside by a spin diffusion. And so one big thing that we really wanted to study here was, if we carbon-13 enrich our diamond, can we then enhance our spin diffusion and our transfer outside? So that's something that I'll talk about later. But before we move on, there were sort of two main ideas that made us feel like this was a really good strategy. So the first idea is that we believed that we could build high polarizations of carbon-13 in diamond because it was sort of known that carbon in diamond has very long nuclear T1 time. And so I have vivid memories of Alex just expressing this, and also from some experiences he had long ago in the past measuring diamond with some collaborators. But I also found some old papers where people studied, or they measured both synthetic and natural diamonds. And this table, for example, shows T1s of hours to days. But this is also at 4.7 Tesla, if we're going to be fair. But what is encouraging is that this table here, this is a paper where they used P1 centers in diamond, or substitutional nitrogen in diamond, which has electron spins, to hyperpolarize carbon in diamond. And the buildup time is typically about your carbon T1 time. And so even at room temperature at 0.3 Tesla, they still found some diamonds which had carbon T1s of a few hours. So this was quite encouraging to us. The second idea is that once we've built a highly polarized carbon-13 ensemble in our diamond, that we believe that we actually could have the polarization transport outside by spin diffusion. And so this is just a model where we'd have possibly particles embedded in an amorphous matrix, where our matrix contains molecules that we actually want to polarize. And we were quite confident that this could work because sort of similar systems have been used to show this phenomenon already. So I gave a few examples of some papers here where I think there are 2 examples where they had crystals embedded in a matrix and they hyperpolarized the matrix, or proton spins in the matrix, and really saw the polarization diffuse inside, and they could distinguish by NMR a hyperpolarized spin state from the surface from a hyperpolarized spin in the bulk, and they could really see that polarization transfer into bulk. This is also an example where they did the same thing, they hyperpolarized spins in the matrix, and then they looked at inorganic particles like tin oxide, which has this really low gyromagnetic ratio nucleus tin, and they were able to hyperpolarize the protons in the matrix, cross-polarize to the tin at the surface, and there they could also distinguish surface sites of tin that are hyperpolarized, and then over time see polarization build up from bulk sites in these tin oxide particles. So these are the inverse case, but we, because this was possible, or because of these studies, we believed it was possible, and we had a pretty good strategy for a polarizer. The next question that we came to was, do we want to use single crystals or do we want to use nanodiamond? This is also a big question. Of course, with single crystal, because the NV energy levels are orientation dependent, you have a big advantage in that you can align the NV axis along the field, and then you get maximum polarization efficiency, and this is a pretty huge advantage. The other is that you can easily optically illuminate single crystals, but I would say the worst disadvantage of single crystals is you have terrible surface area, and even if you're hyperpolarizing, if you are detecting it by NMR, you still need to build a significant macroscopic level of polarization. You can't just polarize nuclei in like a 1 nanometer shell around your sample. So single crystals is really hard because of that. With nanodiamonds, you have high surface area, but then there are all these problems associated with NV centers in nanodiamonds. You have no idea, the surface potentially is covered with electron spins, and you have this big problem of orientation. So because the NV energy levels depend on orientation, the spectrum of the NV, like an ensemble of NVs, could go from 10 megahertz to something like 5.7 gigahertz. And with DNP, you need to be able to excite 1 electron transition with a high microwave power. And getting a source where you can do this with high power over 5.7 gigahertz is, it seems, at least from my experience so far, that this is impossible. But maybe somebody will prove me wrong at some point. So for these reasons, we decided that we would start with single crystals. We would use the single crystal to show that our polarizer is doing what we want it to do, it's hyperpolarizing, and then study nanodiamonds in parallel, and hopefully we'd be able to move to nanodiamonds at some point and really take advantage of that high surface area. So that was our goal. Just to quickly insert NV centers then into the model of DNP that I showed you earlier. So the first thing, of course, is contact. The grand vision that we had were NV centers and nanodiamonds embedded in a glassy matrix with our target molecule, and we'd hyperpolarize the C13 and the nanodiamond with the NV, and then these highly polarized C13 nuclei would transfer the polarization outside by spin diffusion. The magnetic field and temperature conditions, they're pretty much the same. But now that we have the NV instead of just a thermally polarized electron spin, our electron spin polarization can be controlled with a laser, can be controlled optically, versus an electron spin in a glass where you're sort of limited by dynamics of the glass. So that's another advantage. Finally, since we have this mechanism where we have like a relay spin, where carbon is acting as a relay between the NV and any molecule outside, is we have 2 nuclear T1s that we need to care about. So we need a long T1 of the carbon and diamond, and now a long T1 of our target material. So just to summarize this section, we wanted to build a polarizer based on NV centers because they're an optically polarized electron spin, which makes them potentially very powerful for DNP and potentially makes DNP a lot more cheap and accessible. So the route that we chose was we would hyperpolarize the C13 in diamond and then have the spin polarization diffuse to the outside. And for our system, we will start by implementing a system for single crystal diamonds with the goal of going to powders. So just to show you our first iteration of a diamond polarizer, so we want to do DNP, and so that gives us a set of basic requirements. So first of all, we need NMR excitation and detection. We need microwaves to excite these two spin transitions. Now that we have an NV, you know, we get the NV spin polarization through optical pumping. So we of course need a laser. And then since you can do ODMR with NVs, we wanted to be able to optically read out the spin state of the NV, and this sort of helps us better guide our DNP experiment. So we basically used a telescope to collect fluorescence, and then used ODMR to sort of monitor our NV spin state and guide how we should do DNP. So I'll just dive in a bit deeper to the different components of our system. So first, the samples. The samples that we started with are 5 different single crystal samples, one being sorry, the picture quality is so poor. These are the only, or the best pictures I could find from the past. But this is a single crystal HPHC sample with natural abundance carbon-13. And then for carbon-13 enriched samples, we had 4 CVD samples grown from a company called Applied Diamond with a range of enrichments from 10, or including 10, 25, 50, and 100%. Of course, it would have been ideal to have them all synthesized the same way, but we had problems with this with the CVD grown natural abundance sample, and so in the end, that's why we use the HPHC. So these are dense NV ensembles in these diamonds. So we have 1 to 10 ppm NV centers, and you know, the system that we designed is not really at all your typical confocal system. The typical confocal system, you have like a microscope objective which squeezes light and gets you as much power on a small spot of diamond as possible. In our case, we wanted to maximize our C13 NMR sensitivity as much as possible. So instead of using any objective, we illuminated the whole sample. So we just had a CW laser, expanded the beam to hit the sample, and that means that our optical pumping times are much longer. So we have 458 microseconds was one of our max optimal optical pumping times. Also, just to illustrate, so we have these dense ensembles, we're also irradiating them directly. So you could really, like if you filter out, this is our system set up in the electromagnet between the poles of the electromagnet. This is our sample mounted in the system. If you filter out the green light with your laser goggles, you can see this fluorescence with your eyes super brightly. So just to give you an idea of kind of how the setup of the system was. One more thing I wanted to mention is that we also had, so we had this multi-component probe that we mounted in an electromagnet, and laser excitation comes from the side, and then fluorescence collection was done from the back with sort of a telescope. And then the telescope directed light onto an APD, for example. In this probe, we have 2 rotation stages for alignment. So it gave us 2 axes of alignment and helped us easily align our NV axis along the magnetic field. Something else that we did, so instead of normal ODMR, or normal CW ODMR, where you sweep your microwaves while monitoring fluorescence and you just look in dips in fluorescence, we actually did a form of lock-in detected ODMR, this Stanford Research Systems lock-in amplifier. This greatly improved our sensitivity of our ODMR. Basically, we amplitude modulated our microwave excitation, where the modulation was coming from a reference from the lock-in, and then the voltage that we detected from an APD, we put to the input of the lock-in, and this just removes a ton of noise. And therefore, in a single scan, we had an SNR of 100, and in the beginning, we used this microwave loop, which is just a shorted SMA cable, actually, so it's super simple. This also means that we have a really broadband source. So we were able to then acquire the full spectrum of an ensemble of NVs in a single crystal at various magnetic fields, and we could do this quite fast because we had this nice sensitivity. So this was sort of the setup that we had, and also what enabled us with the sensitivity, since it's so fast, is we could in real time align our magnetic field, which was very cool. And then we could also get these nice 2D ODMR plots of a single crystal where we'd sweep microwave frequency, change magnetic field, and monitor the spectrum again. So it not only informs us of how we need to apply microwaves to these NV centers for DNP, but it also gives us knowledge about the sample because we can monitor the ODMR of the sample at different magnetic fields. Just to give you a bit more information about the NMR probe and the microwave excitation. So for our NMR probe, we wanted to fit the whole probe between the poles of the electromagnet. And so if you've ever worked with an NMR probe, typically they have tunable capacitors, so you can tune and match really easily your NMR circuit or your resonant LC circuit. And we were hoping that by compressing everything to this really small system between the poles of the magnet, we could reduce the resistance in the probe and sort of optimize our SNR of our NMR. Everything in the system was really about optimizing the SNR of our carbon-13 NMR detection. So to start, we wound a coil around this 3D printed part. We embedded the wires in epoxy. This protects them and sort of reduces any oscillations of the wires and therefore noise in your coil. Next, we attached this PCB board. So it's a bit messy looking, but this PCB board was used as an alternative to these large tunable capacitors. So if we did it this way, we could fit everything between the poles of the magnet. So this PCB board has a set of pads for matching, or two sets of pads for matching, and one set of pads for tuning. And basically, you can iteratively add capacitors of different levels of capacitance to tune and match. And we basically, if you read this out in a network analyzer and you get the real and imaginary components, or the real and imaginary curves of the spectrum that you get when you look at this in network analyzer, you can sort of predict what capacitance you will need. So this wasn't too painful of a process. So then we took our NMR probe, we mounted this in this aluminum, in one part of an aluminum shield. It's like super simple, but we covered the NMR probe so that it wouldn't create any ground loops with our microwave cable, and I just attached the microwave cable with some duct tape. So this microwave cable, as I said before, is just an SMA cable that's shorted. This loop was about 3 to 4 millimeters. And of course, we wanted to do something more sophisticated with our microwave excitation. That was always in the plan. But this worked to get started with the experiments we wanted to do. And then some students that took over afterwards, looked at, simulating microwave cavities and trying out the first microwave cavities. But for now, this was quite nice, just to at least get some working system where we could start to do experiments and start to get some information. So what I'm showing here is, so we have our NMR probe. We had this sample holder, which looked like a gear that we clipped on top of the NMR coil. So basically, the surface of the diamond that you excite with the laser is right on top of the NMR coil. So that maximizes your sensitivity. And then this, what happens is a timing belt wraps around this gear, and the other end wraps around a gear on top of a rotation stage. And you can use this to as one axis of alignment for your diamond sample. The last step is you close the whole thing with an RF shield, and this reduces noise in our NMR circuit. So with this probe, we could get about 2 microsecond 90 pulses on our carbon, and this is 5 megahertz carbon NMR for operating at half Tesla. So that pretty much covers the system. So our system was designed to operate for DNP at half Tesla, but we could also at least do ODMR at a wide range of magnetic fields. So we have NMR excitation and detection for reading out whatever hyperpolarization we have. And it's designed to work for bulk NV ensembles. So I'll just go quickly through some of our preliminary results that we got before I finished my PhD. So we wanted to study NV centers in C13 enriched diamond. So one of the things we did is when we have these NV ensembles is we did some really simple quantum mechanics simulations to sort of understand what we should expect from the spectra. And to do this, we hope to model the thing with just a 4-spin model. So those 4 spins includes the NV, which is a spin 1, and then the 3 carbons surrounding it in this first shell. So these are the 3 closest possible carbons. They have the strongest hyperfine interaction, which is roughly, on roughly 120 megahertz. And this 4-spin system gives you a 3 times 2 cubed, or a 24 level spin system. And we use these terms of the Hamiltonian to model it. So this includes the Enve-Zeeman interaction, the Enve zero field splitting, about 2.87 gigahertz, the Enve, and then the possible hyperfine interactions. And then for a given enrichment, we would probability weight the hyperfine Hamiltonian. And so what happens is, if you have a, what happens as you add nuclear spins to your first shell is you get sort of this like classic branching diagram. And mostly you see this splitting on the plus or minus 1 states of the NV. So if you add 1 spin, you split this, the single level for both the plus or minus 1 states into a doublet. And then if you have 2 nuclear spins, you have a triplet with a 1 to 2 to 1 intensity ratio. With 3 spins, you have a 1 to 3 to 3 to 1 intensity ratio. And what's not shown in this diagram is this happens for both the plus or minus 1 manifolds. You basically get this 24 level system is basically the 3 NV spin states split into these different manifolds for the different possible combinations of nuclear spin. So for both a 0 to plus 1 and a 0 to minus 1 transition, you'd see a quartet, for example, if you had 3 carbon-13 in your first shell. So what is nice is that this 4-spin system is reflected in the ODMR. So these hyperfine interactions basically determine sort of the structure of the ODMR that you see, whereas as you increase the carbon-13 enrichment, you also get more and more inhomogeneous broadening. So like this quartet is super broad in comparison to the single peak of a 1% natural abundance sample. And so you can somewhat understand the spectra of these NV ensembles in carbon-13 enriched diamond with this model. We of course wanted to do DNP with these samples. So this is the classic DNP experiment that I told you about. So in this case, we fixed magnetic field and we swept our microwaves. And so I'm showing you that experiment for each sample. So we have the 1%, 10% C13, 25, 50, and 100. And what I'm doing is overlaying the ODMR of the NV with the NMR enhancement that you get when you saturate or when you apply microwave CW at this transition. And so what's nice is we get these nice DNP curves for each sample, and we notice that each hyperfine level sort of acts as a source of polarization for the carbon-13 in diamond. So all of these experiments were done at around half Tesla at room temperature. So we wanted to get stats on, what the maximum this very simple polarizing system could achieve. And, what happens is we have pretty strong experimental evidence that the content of each sample is quite different. And so we have this both from the polarization buildup times and from the photoluminescence data. So if you look at the polarization buildup time, one of the first things we notice is that the fastest buildup we get is actually with the 1% or the natural abundance diamond. And so our polarization buildup should be a function of both NV density, our electron spin source, and our spin diffusion rate. So if all of the diamonds had the same number of NVs, then I would expect the 100% C13 to have the fastest buildup. This was one piece of evidence showing that our diamond content varied drastically. Another piece of evidence was the photoluminescence spectra of each sample. So just to briefly recap, so any feature that you see at 575 nanometers, this is the zero phonon line of a neutral NV center, and this broad part is the phonon sideband. And then any feature that you see at 637 nanometers is a zero phonon line of the negatively charged NV, as well as its phonon sideband. So you can see that the 1% diamond has, or the natural abundance diamond has no detectable neutral nitrogen vacancies. It's mostly negative, which is certainly what you want. But then for all of the CVD samples, you have a different ratio of neutral NV to negatively charged NV, and this will certainly just totally randomize our results. So in the end, we didn't get to say, oh, this C13 enrichment is best, but we decided like our strategy at this point would just be to present what is possible with these samples in the system and what we learned from it. So given that, the largest polarization that we could build at half Tesla and room temperature was 0.1%, and this was in the natural abundance sample. So just to recap this part, the ODMR and DNP of NV centers can be understood, or at least in a simple way, from a 4-spin model. We get nice DNP enhancement from each hyperfine resonance in the NV center spectrum, but we're not able to say or give you trends based on the material because we had very large differences in material composition. So this was definitely a big problem that we knew, like, once we got our first measurements on these samples. And of course, the highest polarization we could achieve with this type of polarizer, a super simple implementation, was 0.1% at half Tesla and room temperature. So the last section that I have here are studies of NV centers and nanodiamond powders. So these are all ODMR studies. I would have loved to do DNP of powders, and it was certainly a part of the plan, but we just did not get that far by the time I needed to graduate and move on. So these are just some ODMR studies that I did, of course, with other people in the group. So another student named Kyunhong Jung did all of the experimental studies for this, and I did all of the simulations. So just to tell you, so our sample was, we actually bought nanodiamond powder with NV centers from this company called Adamas Nanotechnologies, and this is super nice because you can just purchase this right off the shelf. So our sample had, their size distribution was centered around 100 nanometers, and they had a density of 3 ppm NV, and you can just buy them as a powder. So we took the powder, basically loaded it into a 4mm NMR tube. We illuminated the nanodiamonds from below and collected their fluorescence with the same, and then we monitored ODMR with the same lock-in detected ODMR technique that I mentioned earlier. So we studied these samples over a broad range of magnetic fields. I put 200 millitesla here, but we actually measured up to 350 millitesla. And we also did some simulations to try to understand the system. And when I simulated this, I took just, again, an extremely simple model because we just wanted basic understanding of the system. And so this model used a Hamiltonian that included the zero field splitting of the NV, as well as the Zeeman term that includes orientation dependence. So of course, with a powder, what is important is really modeling the orientation effectively. So we assumed that each nanodiamond had one NV center. And then what is key for getting the shape of the spectrum right is correctly calculating the probability of having a given orientation in free space. And so something that simplifies this, so this is why I'm showing a diagram of a solid angle, or calculating a solid angle here. So what happens is the zero field splitting is axially symmetric, which means that for each theta that the NV is aligned away from the magnetic field, the probability of that theta occurring is then just the integral d phi around this sphere of three-dimensional space. So this probability is just equal to sine theta, where you get maximum probability at 90 degrees of that, or the 90-degree orientation has the maximum probability, and then the probability of as you go towards 0 degrees just basically vanishes. So pretty much getting this orientation probability is key for modeling these spectra. So I just wanted to show a quick video of if you start with just a single NV center at something like 450 millitesla. So this is the spectrum here. I'm showing this is the 0 to +1 transition here, and this is the 0 to -1 transition. And I just wanted to show how these transitions change as you rotate the NV away from the magnetic field. And so I labeled both of these as, I labeled this one as +1 and this one as -1. You'll see that, I mean, of course, like the NV spin states are mixing a lot as you rotate the NV away from the magnetic field, but I mainly just put it there so you can more easily track the peaks. So I'll play this once. So one thing that you'll immediately notice is that as you rotate the NV away from the magnetic field, the intensity of the transition decreases. And there are probably multiple effects. So, I mean, we didn't include any optical pumping dynamics in these simulations. They were super simple, but in this case, the intensity drops because as the spin state energy levels mix, you get reduced contrast between the 0 and the -1 state. So we called this the ODMR contrast. So what we're showing here is the reduction of intensity of the spectrum just from reduced ODMR contrast. So I'll just play it one more time. So at this point, this is the 90-degree orientation. Right. So that's pretty much what orientation does to the spectrum. So now if you take all orientations from 0 to pi, for example, where you properly account for the probability of that orientation occurring, then you get a spectrum of the powder that actually looks like this. So these are my simulations on top left, and then these are actual experimental data from the sample that I mentioned to you earlier of NV centers in a powder. And it's really nice because like you can really see the shape of the spectrum, and you can see that it's quite similar to what we simulate with just this super simple model. And so this shape that I show you here is called a powder pattern. This is an old term from solid state NMR. So I was informed of getting this correct orientation or probability of an orientation occurring from this problem having already been solved by people in NMR a long time ago. So I just have another video which just shows the effect of adding more crystals. So it basically shows you the process of going from a discrete spectra to a continuous spectra. And I mean, the ideas behind this are pretty simple, but I mainly wanted to show this because videos are fun. So yeah, this is the effect of then adding more and more crystals in the spectra. And so you see that even though the 90-degree orientation has a weaker intensity for a single NV because of poor ODMR contrast, at some point you have enough crystals that this 90-degree orientation starts to outweigh that probability. And so I'll just go back to it real quick. So just to confirm, like our 0-degree orientations are here. They're ones where the MV is maximally split, and our 90-degree orientations are these sharp peaks here, because that's just most of your nanodiamonds are oriented 90 degrees. Okay, so another thing that we learned about these spectra is that the level anticrossing creates different magnetic field regimes. So an NV center, being a spin 1 with a 0 field splitting, has a level anticrossing. It's in both its ground state and its excited state. And we just focused on the ground state. So for the NV, the level anticrossing occurs at about 1,000 Gauss. And so this is where the ms equals 0 and the ms equals -1 spin levels are isoenergetic. So because of this level anticrossing, there are different magnetic field regimes that dictated the shape of the powder pattern. And so we called everything below the level anticrossing the low field regime. At the level anticrossing or approaching level anticrossing was the intermediate regime, where things were maximally complex and your spin states are most mixed. And everything above the level anticrossing is the high field regime. And so just the effect that this has is just that in the low field regime, say 30 millitesla, your NV spectrum is dominated by the 0 field splitting. So the 0 field splitting here is shown at the center, and your Zeeman interaction is a weak perturbation on top. In the high field regime, this is inverted, where the Zeeman interaction is now the strongest and it dominates your Hamiltonian. So the Zeeman interaction is in the center and fixes your spectrum. And then the 0 field splitting is a perturbation on top. So this is what sets the width of the powder spectrum, the maximum width, always to be around 5.74 gigahertz, because it's always going to be twice the 0 field splitting. So this is cool to understand, but awful for DNP. So when you put this all together, like when you actually want to monitor these spectra as your magnetic field increases, this is what you get. So we have experiment on top, we have simulations on bottom. I know I'm going quite long, so I will be done soon, I promise. This is really nice because, again, the simple model really reflects what we see in this simulation, which is really cool. So these transitions here, in this intensity plot, are the powder pattern that I showed you in the high field limit as before. So you can really nicely see the shape. Another feature that we saw is these sets of transitions here. So I'll just explain that quickly. So what this turns out to be is because we have NVs that are misaligned or oriented away from the axis, the energy levels are split, and then we have these weakly allowed transitions between the -1 state and the +1 state. So we're an NMR group, so we call this an old NMR term. We call this an overtone. And the reason why we called it an overtone and not a double quantum is, double quantum, some people would define as a 2-photon transition, where we believed we had our microwave power should be really low. So because of that, we thought we were just exciting a mixed spin state transition with just 1 photon, and therefore we called these the overtone transitions. The last thing I'll say about these data is, we wanted to do DNP with these powders. So what we did was, or what I did in these simulations was, I really looked at the intensity plots of the NV polarizations where red is -1 and blue is +1. And in this diagram on the right, I just changed the sweep width and then looked at what kind of NV polarization we would expect when sweeping over the overtone transition or the single quantum transitions. And yeah, so this we wanted to use to inform us of how to do DNP, but I will just say, we certainly thought about this a lot, and a lot of work was done by later colleagues to try to get to really maximize the amount of the powder pattern that you can excite. Also, people in my group and other research groups thought of the idea that you could go to lower fields. So there's a lot to be done, but this orientation dependence makes it really tough to do DNP with NV centers in powder. I'll just mention some articles from colleagues in my group, as well as colleagues that I'm working with now. And I want to say that these are nice papers on studying DNP of NV centers and nanodiamonds, but it's certainly not exhaustive. I mean, at some point this was a worldwide effort, and I certainly don't want to offend anybody by not including some studies here, but this is for sure, these are at least some examples, that's all that I could easily put up here. Just some final outlook. So, I mean, one big thing for us was which I think is actually a massive effort, is you need really good material control to really be able to optimize the system. And so that means the diamond composition itself with the number of NV, number of P1, and then your C13 enrichment that you can generate. And then, of course, if you want to do nanodiamonds, you need nanodiamonds with reduced electron spins on the surface. So I think that's really important if you actually want to get really nice polarizations. There are certainly easy things we could do with our system to improve it. I mean, we're at room temperature, so obvious thing would be to go to at least liquid nitrogen and boost our nuclear T1. We could also do better in microwave excitation. Like I said, we wanted to go to a cavity at some point, but and do coherent polarization transfer sequences, which would be way more efficient. And lastly, just in terms of outlook of this problem, so at least from what I know, it still seems quite possible to implement a polarizer based on NV centers. But one thing that makes it tricky is if you're going the route of using the C13 as a relay of your polarization. C13 spin diffusion is slow, even in enriched samples. So this probably means that even though you can still gain on your magnetic field conditions, you might be locked in using liquid helium just to make sure your target material has a long T1. So this is a really interesting project, and I certainly don't think it's over yet, but it's a really tough problem for sure. In conclusion, I want to give a huge thanks to the Pines group. I mean, I have an immense amount of gratitude for this group. There's so many people throughout the course of my time there that are just really creative, really knowledgeable, really diverse set of expertise, and just in terms of life backgrounds. So it was a really great experience for me being able to work in that group. I mean, Alex Pines, of course, he's a brilliant professor. He had brilliant ideas that totally guided my project, so I was lucky enough just to work with him. I want to especially thank Chris Basilio and Jonathan King, because they were really close mentors to me. They really, helped, helped make my PhD possible, and I'm extremely grateful to them. I also would like to thank the other people sort of in the Enve group that I worked really closely with, everybody in this list. The students that I worked with, so this is a list of the students that I had while I was at Berkeley who were all like really superstars. They're super knowledgeable and really motivated, and it was a pleasure to work with them. And lastly, this is sort of an aside. I also did a research exchange with the Bloomish group. I never get to talk about that work because it doesn't fit into nicely of the story of studying NVs for hyperpolarization, but it was a really cool opportunity, and I'm really grateful to them. And finally, I would love to thank, of course, Alistair for all of our work together, and for inviting me to this talk, you guys for your attention, especially since I've gone for quite a long time, and would love to thank my new professional family, Envision. It's been a really cool time getting to work with them, and I'm excited about how the company evolves. So thanks a lot for your time, and do you guys have any questions? Also, if you don't have questions, that's of course fine too, but this was pretty nice.
Sorry, I had a quick question. Oh, I see Marva has a question there in the chat.
Oh, okay. All right, I'll take a look. So let's see. I have a question related to your lock-in ODMR. As you can track your NV's frequencies, do you gain complementary information by performing any NMR with these different NV frequencies? Or are you seeing the same information for each NV frequency? So in my experience, we saw the same, I mean, it's interesting experiment to do because you can also kind of confirm that what you're doing with DNP, like if you use the different transitions. So since most of the DNP experiments we did were with single crystals, we'd have peaks for the NVs that are aligned, the 0 to +1 transitions and the 0 to -1 transition. And then you'd also have peaks for the 3 NVs that, or the 3 orientations of NVs that are 109.5 degrees away from the field. So we did DNP at each of those transitions. And if you compare the 0 to +1 to 0 to -1, you get pretty much the same enhancements. I think in our system, in the -1 transition, we got a little bit more, but we believe it was just because at the lower microwave frequency, we had less loss of microwave power. So we got roughly the same enhancement, but then because you're looking at 0 quantum and double quantum transitions, the phase of the spectrum actually switched. So I think if I can effectively switch. So what happened was in these DNP curves, if you compare the 0 to +1 to 0 to -1, pretty much these phases will switch because if like the 0 quantum transition will actually, or I guess the transition on the left will be the higher energy transition. I mean, basically everything just reverses. And then, we also tested the misaligned orientations because we obviously want to know like how much it reduces our polarization to look at and to excite NVs that are misaligned. And so we could still get polarization there, but it was reduced. I think if you go 20 degrees away, then we saw our polarization reduced by 20% or something like that. But thank you very much for the question.
I had a question. Is it possible to use the microwave to sort of encourage spin diffusion? At the end, you mentioned that it was really slow. Are there ways that you can kind of make that process faster?
That's a really cool question. So I didn't actually see papers or look into this until after I finished my PhD, but there are papers on RF-driven spin diffusion or also proton-assisted spin diffusion. And then Carlos Murillas, also, he's a professor at City College of New York who's really been invested in this problem of hyperpolarizing with NV centers, and I worked with him in the Pines group as well. He had a really cool study where he polarized with the level anticrossing of the NV center, and I believe he thought that they were observing it. So because when you polarize with the level anticrossing, you typically polarize the NV, you typically polarize the carbon that's directly adjacent to the NV, but they still saw that they could build up pretty high polarizations, even though a lot of people would say, oh, that spin is so close to the NV, it has a completely different energy. it's too high, so it won't spin diffuse to the bulk. Like typically you need to be in some sweet spot where you're like a bit far away from the NV, but not too far that the coupling is too weak. And so he explained that with some kind of carbon-carbon, or I think, what was it? I think it was a carbon-carbon assisted spin diffusion. And so these assisted spin diffusion mechanisms basically function like you have some sort of two or multi-spin interaction where, like, if you have any energy that's separating the two nuclei that you want to spin diffuse, if some other transition in your matrix makes up that energy, then it will accelerate the spin diffusion that you have. So there are ways that this is done, but I think everything that I know of, it's in extremely specific cases where there was something in that system that like really met that energy difference. And I've been wanting to look into this more deeply and just haven't had to. But yeah, that's a really good question.
Thank you.
Question from Marwa. I have another question regarding your simulation of the nanodiamond ODMR spectrum. How did you simulate contrast? So I have a slide on this, but I realized my talk was so long that I took it out. I hope you guys, or I'll just hit present here. Maybe it will show it. Yeah. So for contrast, we basically had a intensity factor that we estimated from diagonalizing our Hamiltonian. So we would diagonalize this Hamiltonian, that would give us our eigenvalues and eigenvectors. And then with those eigenvectors, we would get the transition matrix element. So that was one factor in our overall. Then we had this factor which we called population difference. And so for the population difference, we took an initial density matrix where we said all the polarization was in the 0 state. And then with our new eigenvectors, we took the difference in the final eigenstate from the initial. So we got a population difference with that term. And then with ODMR contrast, we then got the expectation value of this SZ squared matrix. And then we took the difference in that expectation value for the final state and the initial state. And so we took SZ squared, so the +1 state and the -1 state would be considered equally in that case. They both be 1. So this was how we modeled the intensity of the transitions in the simulation. Hope that answers your question enough. Okay, yeah, no problem.
Okay, I think if there are no more questions, I'd like to thank you for a very enjoyable talk, Anna. And
you're very welcome.
Yeah, I guess that is this QuSCo on Air over.